Video solution from Group 22. Problem 168. Consider a bin with a square cross-section of dimension h by h and length L. The beam is subjected to horizontal traction on the top face as shown. The body forces acting on the bin are negligible. The coordinate axes shown are principal and centroidal. Find expression for the applied force and moment per unit length of bin, Qx and Mx, where x is equal to x3 in the axial coordinate. Also, find expression for the resultant traction and moment, Q and M. Step 1. Find Qx. Qx is the integral of b in dA and plus the integral of t gamma in ds. The traction vector in the top face is as shown. The other faces are traction-free. The body forces are negligible. Therefore, Qx can be reduced as follows. The integral of tau gamma evaluating between minus h over 2 to h over 2. Step 2. Find mx. Mx is equal to the integral of p cross product b in dA plus the integral of p cross product tau gamma in ds. So the position vector p is equal to h over 2 plus e1 plus x2 in e2. We must remember b is equal to 0. Proceeding similarly than in part A, the expression reduced to mx is the integral of p cross product tau gamma in the top face, evaluating between minus h over 2 to h over 2, as shown. So, evaluating from minus h over 2 to h over 2, we can find the vector mx. Then, the expression of mx can be reduced as shown.
Part 3. Find Q, the resultant traction over the cross-section. Upper Q prime plus Q equals to 0, then rearranging the expression, upper Q is equal to minus the integral of Q on dx3 plus the constant C1. Substituting Qx from the expression we found in part A, upper Q is equal to minus the integral of Qx plus C1, and integrating we get the expression as follows. To find the value of the constant C1, we must evaluate upper Q at L where the shear is 0. Therefore, the constant C1 is 0 in E1, 0 in E2, and tau naught L over 2 times H in E3. And substituting in the previous expression, the upper Q expression is given as follows. Part 4. Find M, the resultant moment over the cross-section. Upper M prime plus E3 cross upper Q plus Mx equals 0. Rearranging the expression, we get that upper M equals to minus the integral of E3 cross upper Q plus Mx on dx3 plus the constant C2. From the expression of upper Q that we found in part 3, E3 cross upper Q equals to 0 because E3 cross E3 equals to 0. Therefore, the expression of upper M equals to the minus the integral of mx on dx3 plus the constant c2. Substituting the expression we found in part 2 for mx into the expression of upper M and integrating, we found the expression as follows. To find the value of the constant c2, we must evaluate the expression of upper M at L, where the moment is 0, and we get the following expression. We find the constant vector c2 as follows: 0 in E1 minus h squared tau naught L over 4 in E2 and 0 on E3. Thus, the expression for upper M is as follows.